Hello, this is the luckiest maths teacher in the world. Thank you so much for watching as we go through tree diagrams. These are tree diagrams with replacements. So firstly, what is a tree diagram? So what it is something that helps you list outcomes, and that's really important in probability. We need to know how many outcomes there are and how many ways an event can occur in order to calculate its probability. But we do this with multi-stage events. So what I mean is events that happen in stages. So examples might be if you're tossing two coins and you want to look at the outcomes. The first toss of the coin is one stage, the second toss of the coin is a second stage. Could be something like you roll a die, first stage, then toss a coin, second stage. Or you pick one marble out of a bag, and then you pick a second marble out of the bag. They're the kind of things we use tree diagrams for. So that all they do is help us list outcomes and find probabilities, and that's why we're doing them here. So when I say with replacement, which is what we're looking at in this video, it means that at each stage the outcomes sort of don't change. We'll go through the difference of them and it'll become more clear after we do tree diagrams without replacement in the next video. But let's look at an example of what we'd use a tree diagram for. So, let's look at this question here. I toss a coin 3 times. What is the probability that I toss 2 heads and 1 tail? So at our stage of maths, it might be a little difficult to determine how many outcomes there are in total that could occur when I toss a coin 3 times, and also how many ways you can toss 2 heads and 1 tail. A tree diagram will help us. So what you do is you set up the tree diagram in stages. So if I toss a coin 3 times, there's 3 stages. So I'm going to set it up so I have my first stage in a column, first toss of the coin, second stage, third stage, and you usually write the outcome at the end. So how we draw a tree diagram, we list all the outcomes at each stage. So for the first toss of the coin, I can either get heads or I can get tails. Nothing mind-blowing there. But then if I get heads on the first go, I could get heads or tails on the second go. So that's sort of what I mean by with replacement. It's the same outcomes. It doesn't matter that I got a head on the first go. I've still got the same outcomes available to me on the second go. Okay? Then tails, if I got that first, I can still get heads or tails. But it's the same for the third. If I get heads and then heads, I can get heads, tails, and hopefully you're starting to realize why this is called a tree diagram. Looks a bit like a tree. But all it's done is allow us to list all the outcomes. So to list them all, I just follow the path. So I can go head, head, heads. So that outcome, I'll just write like that. Okay? I could also go head, head, and then get tails. That's another possible outcome. And then I keep doing this for all of the outcomes. And what you should see is there are in fact 8 outcomes, and we'll be able to list them all. So once I've done all of that, I know I can figure out probabilities pretty easily. All of these outcomes are equally likely because at each stage heads and tails is equally likely. So there are 8 outcomes. Each of these has probability 1/8 of occurring. So it's pretty simple to figure out what the probability is that I toss 2 heads and 1 tail. So the probability, I look at how many outcomes that is. So this is 2 heads and 1 tail. I also have 2 heads and 1 tail. Here I have 2 heads and 1 tail. So there are 3 ways that I can get 2 heads and 1 tail, and there are 8 outcomes overall. So the tree diagram just made that a bit easier to figure out. So this was an easier example of a tree diagram, and what made it easy is that each outcome was equally likely. Let's look at a tree diagram with replacement where you don't have each outcome equally likely. So let's have a look at this question here. A bag contains 4 red and 5 blue marbles. I pick a marble, replace it, and then pick a second marble. And I want to find the probability both marbles are the same color. The answer here isn't obvious, and a tree diagram helps us because this is multi-stage, because I pick a marble, then I pick a second marble. So this event is happening in 2 stages. So just like the last one, draw up my tree diagram. First stage gets its own column, second stage gets its own column. Then I write the outcomes, okay? And I'll also write the probability of each outcome. So, first up, I pick red or I pick blue. If I pick a red the second time, there's red or blue again, and if I pick blue, I could get a red or blue on the second go. So these are my outcomes. Red, then red, red, blue, blue, red, and blue, blue. So again, all I'm doing is listing the possible outcomes at each stage. So I've now got 4 outcomes here. So you might be tempted, I guess, to think that the probability that I get 2 reds, probability I get 2 blues is a quarter, right? But that's not the case. This is a bit more difficult because, unlike in the last example, all of these events aren't equally likely because it's less likely at each stage that I get a red marble. The probability of getting a red is 4 over 9, whereas the probability of getting a blue is 5 over 9 because there are 5 blue and 9 marbles in total. So, when that happens, the events aren't equally likely, I write the probabilities on the tree diagram. Now, what makes this a question with replacement is because I replace the marble after I've picked it. So the probabilities are still the same. What I mean by that is, in the second stage, the probability of getting a red is still 4 over 9, because if I pick a red, then I replace it, there are still 4 reds and 9 marbles in total. If I didn't replace the red one, the probability would be 3/8. There'd be only 3 reds left and 8 marbles in total left. So the probability of blue is still 5 over 9. Similarly, if I pick a blue first up, because I replace it, the second time I pick a marble, there are still 5 blue marbles out of 9 in total. So, to find the probability of each of these outcomes, you multiply the numbers on the branches. So the probability I get a red and then another red is 4 over 9 times 4 over 9, which is actually 16 over 81. That is the probability I pick 2 red marbles in a row. The probability of getting red then blue is 4 over 9 times 5 over 9. Same here, blue then red, 5 over 9 times 4 over 9, and then the probability of 2 blues is 5 over 9 times 5 over 9. Now, these probabilities should all add up to 1. In exactly the same way that percentages add up to 100%, probabilities must add to 1. And they do, because 16 plus 20 plus 20 plus 25 equals 81. So 81 over 81 is 1, okay? So this was just a little complicated because these probabilities here were different, as in red and blue didn't have the same chance of coming up, but it's with replacement because the probability of getting a red is the same on each stage. Probability of getting a red on the first pick is the same as getting a probability of red on the second pick, and if we did a third pick, the probability of red would be the same as on the first pick, okay? So hopefully you haven't found that too confusing. So, what is the probability that both marbles are the same colour? So, what this essentially means here, there are 81 possible outcomes. 16 of them involve picking 2 reds. This one here is essentially saying that there are 81 possible outcomes and 25 of them involve picking 2 blues. So, to get the probability that both marbles are the same colour, I could get red and then red, or blue then blue. I just add these up. 41, because 16 plus 25 is 41, out of 81. That is the probability that both marbles are the same colour, either red red or blue blue. So if the question asks what is the probability I get a red and then a blue, red then blue, 20 over 81. Easy as. Alright, hope you've enjoyed this video. This has been the luckiest maths teacher in the world. Have a great day.